Hi everyone, good day. And today we will be presenting our thesis on electrocoagulation of oxytetracycline spiked wastewater and optimization. All right, throughout this presentation, we would actually discussing different points or topics. And first, we would show how antibiotics is really being used. So to start, let's have a short definition of what antibiotics really are. So antibiotics is used for infection for humans and animals. And this medicine have been widely used in various industries, including the agricultural sector. However, in agriculture, as antibiotics has been intaken by animals or been injected to them, this could cause contamination in the future in water effluents actually. So this problem has becoming more prevalent and poses a significant threat to the public health because antibiotic resistance bacteria can survive and spread in various environments. And in order to resolve this problem, actually, studies have been shown about electrocoagulation. So, for treating water effluents, electrocoagulation has been proposed as a potential method for removing antibiotics. Actually, not only antibiotics, but also other organic compounds. So as you can see in this slide, this is some of the studies that have been published regarding electrocoagulation and how it really remove unwanted compounds in wastewater. So this is also used for CO2 removal as well as for antibiotic removal. Okay, so for the whole study, it focuses only on the issue of the antibiotic resistance in wastewater. And today, as we all know, water scarcity is one of the world's problem that we are facing today, and that treated wastewater from agricultural irrigation reuse is being considered as a source of freshwater supplies in developing countries like us in the Philippines. So, therefore, this only highlights that there is really a need for effective wastewater treatment methods to ensure that we could acquire clean water and to ensure that the safe use of water and prevent environmental damage. So, throughout this experimental study that we have accomplished, the objectives of this research are to measure the efficiency of the electrocoagulation and removing oxytetracycline from simulated agricultural wastewater. So, this is also to analyze different parameters such as percentage removal, electrode consumption, kinetic studies, and energy consumption by varying, three parameters: the electrode materials, current, and the additives. So just like what I said earlier, this research aims to serve as a foundation for future research on utilizing electrocoagulation because this wastewater treatment method has been already um, proven its potential to treat antibiotic removal in sewage from the agricultural industry and lessen the environmental effects of the aquatic source disposal.
Several studies have demonstrated that electrocoagulation effectively removes hazardous chemicals from wastewater. Therefore, when utilizing electrocoagulation for antimicrobial wastewater, it is important to consider various optimization conditions. And this study has the potential to significantly increase the efficiency with which antibiotics in wastewater are removed, hence slowing the spread of antibiotic resistance. A fully optimized and cost-effective design may also be attained in this manner. Measurements of percent removal, kinetics, current density, and energy consumptions were taken from synthetic wastewater containing the antibiotics, primarily the oxytetracycline, in a bipolar arrangement for the electrocoagulation setup. For methodology, we have the design of experiment, maintaining constant room temperature and pressure at 100 ppm. The EC tested the OTC using the 3-factorial design. The volume to solution is 3 liters. And the experiment encompasses parameters such as the electrodes, current, and additives in triplicates as indicated in Table 1. Iron and aluminum were anode and cathode electrodes. Using a 30 volts digital DC power supply, zero point 0.1 ampere, zero point 0.2 amperes, and zero point 0.3 amperes were examined. For the additives, we have the sodium chloride, potassium persulfate, and ammonium persulfate, which were also used for chemical dosing to enhance the process of EC and conductivity. For the EC reactor design, as seen in Figure 1, 3 liters of distilled water was used in 3.86 liters glass reactor. All the electrodes vessel have the same dimensions, 100 millimeters by 100 millimeters by 400 millimeters, with an electrode spacing of 16 millimeters immersed in the solution using the aluminum and iron electrodes. To ensure the electrical conductivity in the reactor, the bipolar electrodes were linked in parallel. The iron and aluminum plate electrodes measuring 80 by 500 by 2 millimeters were used in all EC operations, submerging 300 millimeters of length in the solution. The specifications of this model were labeled using the natural numbers. For number 1, we have the hot plate. Number 2, for the sludge outlet. Number 3, the water or solution outlet. Number 4, the reactor. Number 5, electrodes. Number 6, magnetic stirrer. Number 7, alligator clips. Number 8, the power supply. Number 9 is the reactor cover. And lastly, number 10, electrode stabilizer. The reactor was mounted above a magnetic stirrer to ensure an even mixture of the contents for 30 minutes at a speed of 300 rpm. For the analytical method for wastewater sample, the UVV spectrophotometer detected and measured the oxytetracycline. The electrode consumption was calculated by calculating the difference between the electrode's starting and final weights following the EC treatment. The reaction kinetics was assessed by flocculated particle settling time. Getting the current density, it can be calculated from the setup area. In this electrocoagulation study, ANOVA was used to assess the antibiotic elimination and treatment by electrode materials, current levels, and additives.
So, after we accomplish our experimental study, we have gathered data and interpreted the results. So first, let's discuss the percent removal of OTC. So for this section, the results of the EC process were analyzed to determine the effectiveness of different electrode materials. So we have the iron, aluminum, and the combined. So we also have the additives, which is the potassium persulfate, sodium chloride, and the ammonium persulfate. And this parameters have been studied at different current levels. We have 0.1, 0.2, and zero point 0.3. So among the electrodes used, we have found out that the combination of the iron and aluminum really demonstrated significant percent removal of OTC. However, iron electrodes alone were identified to have the lowest concentration. This is this may due to the generation of the metal hydroxide precipitates. So, for the combined, actually, the optimum parameters as the iron aluminum electrodes with the potassium persulfate as the additive and the current of zero point 0.3 amperes. So this really demonstrated the highest percent removal of OTC in wastewater samples with 99.95% removal. And this was achieved at a settling time of 30 minutes. Okay, so moving on, this graph, as you can see here in this slide, it shows a rising trend line and the various charge conditions for each parameter, indicating that an effect of current levels on the electrode consumption. So the red trend shows higher aluminum electrode consumption above 1.5 gram per cubic centimeter, while the combined electrodes consumption remain with the range for applicable conditions. So to sum it up, as the current increases, the electrode consumption also increases. So if you have a current of zero point 0.1 amperes, the electrode consumption is very minimal for just 1 gram within the range of that. It would not exceed to 2. So that's the same for the zero point 0.2 amperes and for the zero point 0.3 amperes. So after we have observed the optimum conditions for the parameters, which is the FEAL electrodes, zero point 0.3 amperes, and potassium persulfate, we did a kinetic study regarding this in order for us to determine the amount of OTC removed during different durations of the EC process. So as you can see in the graph, displays the first order kinetic model, and you can see here the rate constant, which is this one, and the r squared. So therefore, this model shows that first order kinetics were well fitted rather than other models such as zeros or the second order. So the highest rate constant values were observed for the combined electrodes. Okay. So as you can see here in here, this is the graph for the percent removal of OTC during the kinetic studies. So at 5 minutes, 10 minutes, 15 minutes, 30 minutes. And you can see, what you can see here is that the plot reveals that the percent removal of OTC increases with time, ranging from around 30% to over 90%. So here in the second graph, you can see that the energy consumption also rises with time. So actually, it's not really bad because it really has a very low consumption rate from 0.6 kilowatts per hour to 3.6 kilowatts per hour. So this result indicates that the electrocoagulation process can effectively remove OTC from the wastewater effluents, but it comes at the expense of increased electricity consumption. So therefore, this finding highlights the importance of balancing the removal efficiency with the energy consumption. So regarding our statistical analysis, we actually did a plot for the main effects and the interaction plot for percent removal regarding the different parameters. And what we have observed here only is that electrode for the electrode materials, the combined electrodes really has a significant effect on the EC process. And for the current, it really also has influenced the EC process because as you increase the current level, you actually fully remove the antibiotics. And for the additive, um, including or adding chemicals to the EC process has influenced the removal of OTC. And therefore, we also did here is that for NaCl, the ratio for this is 1 is to 2 to the current. So let's say we have 0.1 gram of the NaCl, we would actually have 0.2 amperes of current. You got it? So for the ammonium persulfate and potassium persulfate, both of them have a ratio of 1 is to 1. So if you have 0.1 grams of ammonium persulfate or potassium persulfate, we would acquire zero point 0.1 amperes. Okay, so that's the ratio. And this really um just indicates or really discuss how the parameters contributes to one another.
For the conclusion, after examining the most recent findings concerning the EC's function in wastewater treatments, the increasing significance and promising potential of EC are easy to identify. In particular, EC stands out due to its adaptability in treating a wide variety of wastewater types, ease of installation, and low operating costs. Using the ANOVA with 95% confidence interval, Minitab analyzed the current density, electrode usage, and significant interaction of each parameters used. To remove 99% of oxytetracycline in the synthesized wastewater, the experiment tested three parameters including the electrode material, additives, and the current. Electrocoagulation worked best with Fe and Al electrodes. The combined electrodes having the potassium persulfate at 0.3 amperes and the kinetics determined the amount of oxytetracycline eliminated after different electrocoagulation periods. The best EC reaction time was 30 minutes, yielding 99.9% removal. The aluminum and iron electrode synergy boosts the OTC elimination. The study found out that the EC can work with the removal of OTC within zero point 0.1 to zero point 0.3 kilowatt per hour of energy.